So our next speaker is Paul Baginski from Fairfield University, who talks about abundant numbers, semigroup ideals, and non-unique factorization. Please, Paul.
Okay, so thank you, Mel, and thank you everyone attending. I'm looking forward to next year where we can finally be back together in real life, in person. So I want to talk about abundant numbers and semigroup ideals and how they relate to non-unique factorization. This first slide is probably familiar to pretty much everyone in the audience, but I want to go over it just to get notation down. So if I have an integer a that's greater than or equal to 2, I can add up all of its divisors, and that is a number called sigma of a. And since a is greater than or equal to 2, both a and 1 are divisors. So the sigma of a is at least a plus 1, but it can be quite a bit bigger. We fall into 3 cases. A is abundant if this sigma of a is bigger than 2a. A is perfect if sigma of a is exactly equal to 2a. And a is deficient if sigma of a is less than 2a. Roughly speaking, this is abundant numbers have a lot of factors, deficient numbers have very few factors, and perfect numbers have just the perfect amount of factors. I've listed out the abundant numbers here, and then below that, I've listed out the non-deficient numbers. So this is abundant and perfect. The perfect ones are here in red, 6 and 28. And the next one's considerably bigger. It's not known that there are infinitely many perfect numbers, and it's not known that there are any odd perfect numbers. But basically, I'm going to concentrate on abundant numbers, but everything that I say in this talk is also true about this set D non-deficient numbers. The abundant numbers, the first few are all even, but there are odd abundant numbers, 945 being the first one. And if you want to work with odd abundant numbers, which I did, you start working with really big numbers, and that becomes difficult. And so in general, I want to sometimes restrict which primes I'm looking at. So if I have my favorite set of primes, say that's regular P, usually this will be a finite set. I want to restrict and look at only the abundant numbers that are made out of primes in P. Okay, so that's saying that the support of the abundant number is in P. So for example, if my favorite set of primes is 3, 5, 7, I'm looking at the abundant numbers that are some number of 3s, some number of 5s, and some number of 7s. These exponents can be 0, so I don't have to use all of the primes. I'm just requiring that all my primes in my prime factorization are in this set P. Now, if I choose my set of primes poorly, I can end up with an empty set when I do this restriction. So there are no abundant numbers that are prime powers, meaning that if I only allow one prime in the support, this restriction is automatically going to be empty. And there are no abundant numbers that are odd that have exactly 2 primes in the support. So there are no, if P and Q are distinct odd primes, then there's no abundant number of the form P to the K, Q to the L. And that means if my set P is size 2 and it's both primes are odd, then this restriction is empty. And in general, as you start throwing away primes and you require this P to have larger and larger primes inside it, then you need more and more distinct primes inside P in order to get any abundant numbers. So in order to guarantee that this restriction is non-empty. So basically, if I wanted to consider primes bigger than 100, I need to use a lot of them to get any abundant numbers. And this is because of early work of Dixon. So interest in abundant numbers really kind of took off in the beginning of the 20th century with Dixon's work. Dixon was interested in the smallest abundant numbers. So smallest how? Under divisibility. So he called an abundant number primitive if the number is abundant, but no factor of that number is abundant. So these are the smallest abundant numbers under the divisibility relation. And he proved that if you restrict the number of distinct primes that you're working with, say you're working with exactly R distinct primes, then there are only finitely many odd primitive abundant numbers that use that many distinct primes in their support. This is a really strong statement. This is kind of, it's a little hard to wrap your head around the first time around it because it's a double finiteness condition. So it's saying if I choose a set of size R of primes, and I look at the abundant numbers made out of those primes, there's only finitely many primitives in that set. But on top of that, if I range over all such R-size subsets of the primes, this whole union has only finitely many odd primitives. So I'm not restricting to a particular set of primes. I'm running over all R-size subsets of the primes, and I only get finitely many odd primitives in this entire huge set. Now I got interested, oh, and this was proved, this was where Dixon proved Dixon's lemma. So if you're in combinatorics and you've heard of Dixon's lemma, this is that paper where that was proved. Okay, so I got interested in this when I was attending a CANT talk a few years ago, go CANT. And this was kind of a throwaway comment in someone's talk. It wasn't the main focus of the talk, but it was something that I didn't know about abundant numbers. And yet it's really relevant for my own research. So I think everybody knows, if you've taken number theory, that sigma is a multiplicative function. But there's an additional inequality that I didn't know about, which is that if I take two integers and I look at sigma of AB, that's greater than sigma of A times B. I guess this should be a greater than or equal if one of them is 1. But you can take that inequality and stick an additional inequality on there. So if I was assuming that A was already abundant, then sigma of A is bigger than 2A. So I'd get 2AB is less than sigma AB is less than sigma of the product AB. And that means, looking at the front and the back, that means that AB also is abundant. So if I take an abundant number, multiply it by any B, I get another abundant number. I did not know this property of abundant numbers. So what this means is that the abundant numbers are closed under multiplication. Actually, more than that, they form a semigroup ideal in the natural numbers. And so just the fact that we have a semigroup, that already means I can do factorization theory on it. The fact that A is an ideal, that's added icing on the cake, but it's a really important property, as it turns out, for the factorization structure. So what does it mean when I'm saying that I want to do the factorization structure of A? What I'm going to do is I'm going to take abundant numbers and I'm going to factor them, but not into primes. I'm going to factor them as products of other abundant numbers. So I'm breaking up an abundant number into smaller abundant numbers. And the minimal elements under this breaking up process are the irreducibles, or if you attended Scott's talk, the atoms. So an irreducible is an abundant number that cannot be written as a product of two abundant numbers. Okay. If we look at the list of abundant numbers, a lot of them in this list are irreducible. So 12, being the smallest abundant number, is irreducible because it cannot be written as a product of two abundant numbers. But even something bigger like 40, it cannot be written as a product of two abundant numbers. You look down the list, there's a 20 there, but then you need a 2, and 2 is not abundant. Okay, so there's no way to write 40 as a product of two irreducibles. That means 40 is also irreducible. And actually, I think every number listed here is irreducible. And that's because the first reducible element of A is the smallest product of two elements of A, namely 144. Okay, so irreducibles are the smallest atomic abundant numbers, in the sense that they cannot be broken up as the product of two abundant numbers. Well, we had another notion of smallest, and that was primitive abundance. and that was a number was primitive abundant if no factor was abundant. So if no factor is abundant, then in particular, you can't find two factors that are abundant whose product is A. So that means if A is primitive abundant, then A is irreducible. But the converse is false. So 40 had 20 as a factor. And so that meant that 40 is not primitive irreducible. It had an abundant factor, but we already argued that 40 was irreducible. So this is a one direction implication. So that means the irreducible abundant numbers, it's a broader class of kind of small abundant numbers. So then the question is, Dixon proved that if you range over all the primes, subsets of the primes of a fixed size, and you look at all these restrictions, you get only finely many odd primitives. And in particular, any one of these restrictions has only finely many odd primitives. So the question was, how many irreducibles do we have? Do these only have finely many irreducibles? That would mean that they're finally generated, or do they have infinitely many? And I initially thought they must have finely many. I could just use Dixon's lemma again for the same proof, but it's actually incorrect. That logic was wrong. It turns out that every one of these restrictions, A sub p, contains infinitely many irreducibles. And so all of these are not finally generated, and that means that the factorization structure already is pretty interesting. Why does Dixon's lemma not work? Well, Dixon's lemma applies to the standard ordering of the natural numbers under this divisibility relation. But here I'm doing divisibility by elements of A. It's a different partial ordering. So Dixon's lemma doesn't apply for that non-standard partial ordering. Okay, so now that I know that I've got infinitely many irreducibles, I can start trying to factor abundant numbers as products of irreducible abundant numbers. And you quickly find out that this factorization is not unique. So I can write the same abundant number in multiple ways as products of irreducible numbers. So 24 times 24, it can be rewritten as 12 times 48. So this is two irreducibles on the left, two different irreducibles on the right. Now you may think, okay, well, I'm just kind of like shifting things around and I'll always have the same number of irreducibles, but actually you quickly find that the number of irreducibles is not preserved. So that means that we're not half factorial. So here's an example, 18 times 20 times 24, that's 3 irreducibles on the left. That can be rewritten as a product of 2 irreducibles. And all these examples so far are just even abundant numbers, but the same thing happens with odd abundant numbers. Taking that smallest odd abundant number, if I raise it to the third power, so this is 3 irreducibles on the left, I can rewrite it. Both, you'll have to believe me, both of these numbers on the right are irreducible abundant numbers. So I've taken 3 irreducibles and rewritten them as 2. As soon as you get different factorization lengths, factorization theorists like to collect them all into something called a length set. So this is just all the different factorization lengths of an element. So we're counting, if we look at each factorization of the element, we just count how many irreducibles are in that factorization. So for instance, 945 cubed, we had a factorization here on the left as 3 irreducibles, so 3 is a length. And we had a factorization on the right that was 2 irreducibles, so 2 is a length. And so that means 2 and 3 are in the length set of 945 cubed. And you can argue that those are the only 2 possible factorization lengths. Now, generally, if you're working in kind of a more familiar example with non-unique factorization, like an algebraic numbering, if I take 100 irreducibles and I mash them all together and take their product, that might be rewritable in several different ways, but generally that 100 is kind of like an anchor and you can't go very far smaller or very far bigger. So the kind of the length set is kind of anchored around 100 in a pretty restricted range. Turns out that with these abundant numbers, you get quite a different behavior. And the behavior that you get is something called Bifurcus. So these a Bifurcus semigroup, this was something that wasn't studied for a long time because people didn't know of examples, and the examples weren't really that relevant, but more and more examples have come up. So a Bifurcus semigroup is a semigroup in which every reducible element can be written as a product of two irreducibles. Meaning, no matter how many irreducibles I multiply together, there's always a way to rewrite that as a product of just two irreducibles. Okay, so there's complete collapse down to as small as possible. All these atoms multiply together and they reduce down to just two. And this is very different from what you see in algebraic number rings and polynomial rings, in any sort of kind of standard examples in non-unique factorization. And it turns out that a lot of these restrictions, A sub p, end up being Bifurcus. So I have this theorem that if you look at one of these restrictions AP, and there are distinct primes Q and R such that every abundant number in AP is divisible by Q and R, so they have Q and R in the prime factorization, then this restricted set of abundant numbers has to be Bifurcus. So here's an example. P is the set 3, 5, 7, 11. So I'm looking at abundant numbers out of those 4 primes. And it turns out that every abundant number that you make out of those 4 primes has to have a 3 in it and has to have a 5 in it. So that means this restricted set of abundant numbers is contained in the multiples of 15. And by this theorem, that means this AP is Bifurcus. So every abundant number in the set can be rewritten as just a product of 2 irreducible abundant numbers. Now this theorem is nice, but it doesn't apply to every example of abundant numbers. So if I just threw in an additional prime 13, then this hypothesis fails. These numbers A, B, and C are all abundant, but they don't share the same 2 primes in their prime factorization. They all have a 3 in the prime factorization, but then if you look for another prime, there's not another one because A doesn't have 11 or 13, B has no 7s, and C has no 5s. Okay, so this theorem does not apply. This theorem tells us nothing about this AP. And actually this AP, I believe, is not Bifurcus. I believe it is something called 3-furcus or trifurcus. And so what is that? Well, once Bifurcus started gaining traction, people tried to generalize to higher order sort of furcus, and there were competing definitions. I think these examples from abundant numbers are going to kind of tilt the debate in one direction towards this definition. This is not my definition. This has already appeared. So a semigroup is M-furcus if every reducible element factors as a product of at most M irreducible. So I multiply a whole bunch of irreducibles together, it collapses down to something of size at most M irreducibles. And Bifurcus is just a special case of 2-furcus. And I proved that if you look at these abundant numbers, you get this M-furcus property all over the place. So if I take my favorite set of primes and I restrict to that set of primes, this restricted set of abundant numbers is going to be M-furcus for some M, and that M has a nice bound. It's at most the size of my prime set plus 1. And this is a sharp bound. So you can get APs that have M exactly P plus cardinality of P plus 1. Now, this theorem on its own says that each set of primes has some M, but it could be the same M for all the sets. So it could be that the whole set A is M-furcus, but that's actually not true based on the next theorem. So the next theorem says that for every M, I can find an element, an abundant number whose minimum factorization length is at least M. So this element A cannot be written as a product of fewer than m irreducible abundant numbers. And that means that this A is not Mfurcus. In fact, I get sort of larger and larger m's. So for every m, I can find a finite set of primes such that that restriction AP is L-furcus, but not L-1 furcus for some L greater than or equal to m. Okay, so I can keep going up. Now, ideally, I would like L to just be equal to M, but that's currently still a conjecture. I think I can prove it, but it requires a lot more argument. So what I'm getting is kind of a tiered structure here. If I look at all the abundant numbers, all these localizations collapse a lot, collapse down to product of M irreducibles, but these M's are varying as I vary the set of primes that I'm looking at. And I was generally calling this a multifurcus structure. And I noticed that when I proved these theorems here, I really wasn't using a huge amount of information about abundant numbers. I was really kind of using the fact that the abundant numbers were an ideal and just some peripheral properties. So it really didn't seem, it seemed like something that was ripe for generalization. So I started trying to find similar monoids where I can kind of create this multifurcus structure. So the abundant numbers were a semigroup ideal inside the natural numbers. That's a free abelian monoid on the primes. You can work a little bit more generally in factorial monoids. The only difference is I have a free abelian monoid on some set of primes, not necessarily the integral primes, just some prime generators. And I can add in some units. It's just a slight bit of additional generalization. And I'm going to look at a sub-semigroup of this F, and I'm going to say it's multifurcus if every restriction H sub P is going to be M-furcus for some M. And basically using the same methods that I had for abundant numbers, I prove that if H, you need two ingredients. If H is a semigroup ideal and it's power free, meaning that it has no prime powers in it, then H ends up being multifurcus. So that means each one of these HPs, things collapse down to level M, and this varies potentially as a set of primes varies. Now, multifurcus allows a uniform M here, so it allows M-furcus monoids are multifurcus. So I need additional conditions to get this sort of tiered, that the M needs to vary with the set of primes. But kind of this theorem is really powerful because the hypotheses are so simple. All you need is an ideal and you need it to be power free. So I started looking at generalizing abundant numbers to other nice sets. So abundant numbers, you had sigma of A was greater than 2A. Same arguments work for non-deficients. So that was greater than or equal to 2A. I first could change this constant from 2 to something else. And if I take a constant C that's greater than or equal to 2, I require sigma of A to be greater than CA or greater than or equal to CA. So kind of higher levels of abundance. Both of these turn out to be ideals and both end up being power free. So that means both of these end up having this multifurcus factorization structure. If you choose a C that's less than 2, you break one of the properties. So you really need C greater than or equal to 2. Otherwise, you don't get ideal or you don't get, I think you don't get power free. Okay, and then how else to generalize? Well, I've got this function sigma, and I've also got another function, the identity function on the right-hand side. Those are both multiplicative arithmetic functions. Maybe I can replace them with some other arithmetic functions. And all I need is to guarantee that the resulting H is a semigroup ideal and it's power free. So here are some nice examples. Let's say your favorite arithmetic function was the Euler's totient function. Well, now, if I look at all the natural numbers whose Euler's totient function is less than CA, for a fixed real number C less than or equal to half, this ends up having a multifurcus factorization structure. So these totient numbers collapse down into products of M totient irreducible function elements. Again, C needs to be less than or equal to 1/2. Otherwise, you start breaking either the ideal property or the power free property. And this one's sort of downward closed, right? So here the weird function was on the left and the identity was on the right. Now the weird function's on the right and the identity is on the left. Totient function is multiplicative, but you can also do additive functions. So I need to, if I take omega of A greater than or equal to 2, so these are all the elements of the natural numbers that are not prime powers. So this is pretty clearly an ideal, and it pretty clearly excludes all powers, so it's power free. This is also has a multifurcus structure. And again, I could change this constant from 2 to k, so I can look at all the natural numbers with at least k distinct prime factors. This is also multifurcus. And this example is really, really interesting for factorization theory for a lot of the algebraic properties. So I've mostly been talking about, so I've been talking about kind of the arithmetic properties. What I've been working on the last couple of months are algebraic properties. So I'll get to those in a moment. The question that I have is, I need, in order to use my multifurcus theorem, I need to have some arithmetic functions f and g and some real number. And I look at this set. And in order to use my multifurcus theorem, I need to make sure that this set is a semigroup ideal and it's power free. That characterizing those arithmetic functions and the real numbers that do this, those triples, that seems like kind of a hard question, but I'm sure that there's some nice properties that you can quickly get, like infinite families for functions f and g and c that make these sets fit those conditions, semigroup ideal and power free. So last thing that I've been working on is.
Yeah, Paul, you need to finish up quickly.
Okay, algebraic properties. So I'm not going to explain any of these definitions, but basically, if I'm working with a semigroup ideal and a factorial monoid, so this general condition, I've answered a lot of questions. So root closed, complete characterization, semi-normal is equivalent. Completely integrally closed is basically impossible, and that means also crawl is impossible. And then the real big one is that C monoid. So this is defined using an equivalence relation. I've given a nice simpler equivalence and also a complete characterization. So if you're a semigroup ideal that's a C monoid, you have to look like a certain form. I can give an explicit definition. So that is all I have to say. Thank you.
Thank you very much. So there is one question in the Q&A from Noah Liebowitz Lockhart. He asks, are there bounds on how small bifurcus sets can be? Do they have to have positive density?
So for the abundant numbers, every time I'm doing a restriction, I'm doing a restriction to a finite set of primes. So the density is kind of, I'm not sure where the density would come into there. Or are you saying that, so I think I can find arbitrarily large subsets of the primes that are bifurcus. I don't know if that's the question that you had.
Okay, Paul, thank you very much.
Okay, all right, thank you.
And the next talk is in 2 minutes. So Joseph, if you want to share